So good evening everyone. Let us start after uh, quite a long break. So before the break we have discussed on what do you mean by system, taking the example of a DC motor, what are the different components like different parts of a system like uh, what are the input. Any system will have certain inputs and certain outputs. So for a DC motor, we have discussed that the field voltage, armature voltage, they are like the inputs that you give to that you excite your system with, and the output that you generally observe is the speed. Now, in order to we discussed about the mathematical model of a system. So any system that is a physical thing, and if we represent the physics of the system through mathematical equations, that becomes the mathematical model of the system. So it's basically some set of equations that relate the inputs to the outputs, uh, and also it includes certain states, what are called as the state variable, that is specifically for dynamic systems. And also you have parameters. So variables, parameters, all those things we discussed. Parameters are those quantities of the system whose values generally remain constant, or almost constant, can be approximated to be constants throughout the operating time. And the variables are the quantities whose value change during the operation. So why are mathematical models needed? That also we have discussed, that if we want to analyze the behavior of the system, we need mathematical model. If we want to predict the response, then also we need. If we want to design certain controllers, say we want to any system can have its own response, but if we want to change the response, then as per our wish, then we can use some controllers, and in order to design controller we need the mathematical model of the system. Also, if we want to simulate any system and see its response, then also we need a mathematical model. And also optimize performance. Suppose we need some output, but we have different sets of inputs which can lead us to the same speed. So for an example here, we can have Vf, we have Va, and we have some omega speed. It is within the base speed, the desired speed is within the base speed, then typically Vf, that is kept constant at the rated voltage, and we only achieve the speed through controlling the armature voltage. But that is not the only way to do it. We can also reduce the field voltage, and we can have some, so say Vf1 comma Va1, that can lead us to the same the speed. And also we can have different combinations of inputs that can lead us to the same speed. So if we have such a case, then a question arises that which set of inputs is better for us. Then it comes to optimization. Optimization is typically done for taking some cost function, which is typically efficiency, because efficiency is related to cost only, energy lost during operation. So we will, if we have some model of losses, then it is of interest to look at which set of inputs give us or leads to a higher efficiency of the system. Then we will operate the motor at that with those inputs. But in order to predict that which operating point leads us to our desired efficiency zone, we need to have a mathematical model of the system. Then only it will be possible for us to optimize the performance of the system. So in a nutshell, we have if we know what are the inputs, if we know what is the current state, what are the current states like state variables, and if we know the parameters of the systems, then it is possible for us to predict the future states, the future uh, values of the state variables and as well as output. So output is typically one of the state variables, mostly in case of dynamic systems. So you can look at the differential equations for a DC motor. So the first equation, well known, this is the field voltage KVL equation. Then next is the armature circuit KVL equation, and the next is the mechanical subsystem equation, where you have the electromagnetic torque, you have frictional torque, you have inertial torque, and you have some load torque. So these set of differential equations represent the is one form of the mathematical model of the system. So next, we also briefly touched upon the different forms of differential equation model. So this is one way to represent a system mathematically. Then also uh, we can have something called as state state space model. Already I have talked about the states. So state variable is something, uh, if you know the value of that, if you know the value of that state variable at a given instant, if you know the future input, it will be possible for you to predict the future output. That is the definition of the state variables. So state variables are typically those quantities whose differentiation is being carried out in the differential equations. Like in this case, if there is a ddt time differentiation happening of if, so if is a state, ia is also a state, and omega is so these are the three states for this system of dc motor. Similarly, for any other system, you can have different number of states. So if you so there is a specific way of representation of the system using the states of the mathematical model. So that is called a state space model. We will review that briefly. Then of course the next one is, so the first one was differential equation model. This is difference equation model. So what is that? It is nothing but the discretized form of differential equations. So if we want to have a digital implementation of our system, like simulation in a computer, then we need to discretize the system. So for that, this model is very useful. Also, if you want to implement your controller in a digital signal processor or DSP kind of a platform, then you need to take your you need to finally implement the controller equations in the difference equation model. It is not possible to implement the same in continuous time, because in digital signal processor there is nothing like continuous time. There is some sampling happening and any decision is taken only at the sampling instance. So it's about discretization. So difference equation model, that is another uh, very useful model. The transfer function model. So transfer function model basically relates the inputs to the outputs, considering all initial conditions to be 0. So we'll discuss, and actually it is quite popularly used in controller design in frequency domain. So transfer function model is for frequency domain. All the other ones, so differential equation, that is time domain, continuous time domain. State space model also continuous time domain. Difference equation is discretized time domain, and transfer function model is frequency domain. So what does it mean? You need to relate the input and output and with some magnitude and phase. So suppose input, so transfer function model is only valid for LTI systems. We will discuss in details what do we mean by that. LTI, L stands for linear time invariant. So a system which is linear time invariant, for that, if your input is a sinusoid, then your output is also has to be a sinusoid. But input and output will have some, we can have some magnitude difference, and also they can have some phase difference. So say this is input and output can be something like this. So obviously if this is the magnitude say m1 and this is the magnitude m2, then there is some ratio m2 by m1. So that is the gain of the system, and it also has certain phase difference. So it is the output. So if this is the input and this is the output, then the output is lagging input by certain angle, say phi. Then it has some minus phi as the phase delay. So this is basically the gain and phase relation of a linear time invariant system in transfer function in a transfer function model. So because the frequency is what, so if you have, so in for this case it has some time period, and 1 by t is basically frequency. So if you keep on changing the frequency, this magnitude, whatever gain you are having, and that phase, that can change in a linear time invariant system for different frequency. So we describe such a thing using gain and phase plots with frequency, also popularly known as the Bode plots, and are quite well known to be used for controller design for linear time invariant systems. And also one catch is because it's very uh, easy to design controllers, and also it is intuitive compared to the other models. Typically, even if we have any nonlinear system, even if we have some nonlinear system, there is a we want to linearize the system. So linearization is done around one operating point. So the nonlinear system is represented as a linear system local to the operating point that we want. And once we get the linearized form of the nonlinear system, then we can apply the transfer function based model on controller design to design controller, and that can work reasonably well uh, for certain system where the nonlinearity may not be that much significant, or yeah, for certain cases it works. So there is a systematic procedure to design controller for nonlinear systems also, which work reasonably well. So transfer function model and the frequency domain controller design, that is what we will discuss mostly for our DC motor, but we will understand that uh, we will understand about linearity, time invariance and other things. And also we will discuss the difference equation model, because that is really important if we want to implement it in any digital signal processor, DSP. So typically what is done is, if you are given a system, we will design the controller in the frequency domain, that is using the transfer function of the system. And after we get the controller, we will transform the controller into its difference equation model. So we'll take care of certain things which comes up due to discretization. We'll take account of that, and we'll modify the controller in a certain way. And so we will design the controller in the transfer function model, using the transfer function model in the frequency domain only. But after that, whatever controller CS we obtain, that will be accounted, that the discretization effect will be taken into account in this one, so that the difference equation of the controller will be derived, and that will be implemented in any DSP processor. So let us go one by one and discuss and understand what these different forms of mathematical models are. So the first one is differential equation model. I think this already we have discussed quite a lot number of times. So this is for the field circuit KVL equation. For the armature circuit, it will be VA equal to LA DIA dt plus RA plus EB. Then mechanical domain, we have the electromagnetic torque is equal to inertial torque plus frictional torque, represented here as proportional to speed, and we will also have the load component of torque. And we also have two equations relating this electromagnetic torque to current and back EMF to speed. So we have two static equations. So these three are dynamic equations because you have some time derivative involved. But so dynamic equation means so only the present input is not sufficient for you to predict. Only the future and inputs are not enough for you to predict the future output. You also need some other additional information to for a dynamic system. But for static, if the system is static, or if you have static equations, then only the present input is enough for you to tell about the present output. So like k if into omega. So if you know speed at any instant of time, you know the back EMF, because there is no dynamic thing involved between the two. So obviously we have to assume that if is constant, otherwise this is not a linear equation, this becomes a nonlinear equation because there is multiplication of two state variables. So if and omega both are the state variables of the system, and in any nonlinear system is there cannot be any multiplication of two state variables. So actually it's a nonlinear equation. But if we assume under steady state approximation that there is no transient in the field circuit, so if has actually reached capital If, which is the steady state constant value, then Eb is equal to k into capital If into omega, where it becomes a static equation where back EMF is directly proportional to speed. Similarly, for electromagnetic torque also, under the same assumption that If has reached steady state, you will have Em equal to k into If. This whole thing can be considered as a constant number into Ia. So if you know current at any instant of time, you know the electromagnetic torque. So this also becomes a static equation under the assumption that there is no dynamics in the field circuit. Already the dynamics have settled down and your field current is reasonably constant. That is why also when I showed you the MATLAB Simulink implementation of the model of the DC motor, first the field voltage was excited, field circuit was excited with some voltage, and we waited till the time field current reached to steady state. Only after that we introduced some voltage in the armature circuit. Then so that is the way you, when you are operating your DC motor, that is the way typically lab assistants or TAs tell you to operate in a lab. First give the field excitation, then slowly give the armature voltage excitation. That's all. That is the differential. So this is the differential equation model. So I hope it's clear. And next is the state space model. So so first let us understand the form in which uh, the state space model is expressed. So say X, capital X, is a matrix with all the state variables, and x dot means the rate of or the time derivative of the state variables. So this is expressed as a function of the state variables and the input. So this is the first equation. So x is state matrix or state variable matrix. Say if you have x1, x2, x3, some number of states, your capital X will actually be x1, x2, x3. This is a column matrix. Then what is the U? U is the input matrix. Suppose you have certain number of inputs, say u1, u2, you can have different inputs. So U matrix will be again a column vector u1, u2 say. And x dot, what is x dot? X dot is nothing but the time differentiation of the different state variables. So dx1 dt, dx2 dt, dx3 dt. So if we have three state variables, x dot is nothing but this. So the first equation in state space representation is this. X dot is represented as a function of the state variable matrix X and the input matrix U. So this is the first equation, and the second equation is the output matrix. Output matrix is expressed as a function of, again the same thing, state variables and input. So what is the uh, what is uh, the output matrix? So this is Y is basically the output matrix. So if you have different outputs, say y1, y2, then this Y matrix will be nothing but a column vector of y1, y2, and x and y u I have already defined. So any model, when it is represented in this form of two matrix equations, it is called as state space model. And there is a whole different algebraic or matrix manipulation for this representation of the system. So there are different types of mathematics done, control theory developed around this state space model, and also there are control techniques like uh, what is that called, linear state feedback type. So you feedback some state, and based on that you design some controller. Also there are some things like controllability, observability. Controllability is whether you can control a specific state as per you desire. So that is defined as controllability. And also observability, if you given a state, are you actually capable of observing it, or that is measuring it and taking feedback, are you actually capable of doing that? So there are so all these things are mathematical definitions, I will not go into that, but at least how given the model of the DC motor, how to represent our DC motor model in this state space model, that briefly we will do. So for doing that, what do we need to do? So let us consider the state variables. So what are the state variables in our DC motor? We have the IF, we have the IA, and we have the speed. So these are the three state variables for our DC motors, right? What are the inputs? We'll consider only field voltage and armature voltage as the inputs. And also another thing that comes, that is not directly as decided as one of the inputs, but it is kind of mechanical input which gets applied on the system based on the mechanical load it tries to drive. So TL, load torque, also is one of the inputs. And we have output. So let us define only the speed as the output as of now. So we have three state variables, if, ia, omega. We have inputs like vf, va and tl. Out of these vf and va can be called as the control inputs because we will be actively controlling them or changing them to require to finally derive the output speed, where this tl is called as the disturbance input because that will be disturbing uh, our our disturbing us in the way of on the way of reaching our output. So we may not know what this TL or how this TL will vary, but we nevertheless we would like to reach the speed that we want. So that is why, because it is not well known to us or may not be well known to us or directly in our within our control, but it is disturbing us on the way to reaching the desired output. That is why typically it is termed as disturbance input of the system. And the other things which can be directly controlled by us, that is we can obviously control the voltage because that is what we are applying to the motor. The load is something that we need to the motor needs to drive, that is not directly under our control. So these are the control inputs. Vf and Va, and omega is the control or the output of the system. So let us, and state variables already we are clear, if, ia and omega. So let us just write the equations in proper form so that we can represent our DC motor model in this form. So let us start. So the first equation I will just rewrite it, Vf equal to Rf if plus Lf dif dt. How can we rearrange it? We want to take the differentiation term of the state on the left hand side. So dif dt will have, and this if so this will become negative, so this will be Rf by Lf into If, then plus 1 by Lf Pf. Is it correct? Yes. So this is the first differential equation that we have. The next differential equation, if I do for the armature circuit, then this is Va equal to La dia dt plus Raia plus Eb. I'll write Eb as, say, I'll write Eb as some constant, say, or yeah, K into If into omega, right? So dia dt, that can be written as minus Ra by La into Ia. This is this term. Next we have uh, minus K by La into If into omega plus 1 by La into Va. This becomes our second equation. Let me quickly check it. I dA dt 1 by L, this will become negative, this will become negative, and this will remain positive. That is correct. And the third equation is basically electromagnetic torque, that is K into If into Ia, that is equal to J d omega dt plus B omega plus load torque. Let me write it in appropriate form. D omega dt is equal to minus B by J into omega plus K by J into Ia minus 1 by J into TL. Right? Is it correct? J remains in this side, So this becomes positive, this becomes negative, this becomes negative. This is correct. So these are the three equations written in appropriate form for us to represent in the matrix form. So let us write the state variables like first equation. So we will simply write it in the form. So dif dt, this is the first one. Second one is dia dt, and the third one is d omega by dt. So this is like the left hand side of our first state space model equation. Then we will need to have some matrix, we will decide that later, and we will have to multiply it by the three states. So the first state is if, second state is ia, third state is omega, right? Then or okay, so this becomes matrix representation. So we so all systems may not be it may not be possible for all systems to represent in this matrix form. So what I am telling here is these equations like uh, this f1 of x into x comma u, this cannot, this may be separated, like for certain cases this f1 as a function of u x and u, that can be written in this form, some matrix a into x plus some matrix b into u, where a and b, these are matrices. And similarly f2 xu, for some cases it can be written in this form of c into x plus d into y, where c and d are again matrices. So for all cases it may not be possible for us to write these functions in this form, but for some cases it is possible. So the mathematical models where it is possible to write the f1 and f2 functions separately using a matrix, b matrix, c matrix and d matrix, where the state contribution and the input contribution can be separated out, and similarly in the output also state contribution and input contribution can be separated out, those systems are linear systems. So this format is possible only for linear systems. Additionally, this a, b, c and d, this a, b, c and d, the matrices are separately describing the matrices are possible only for linear systems, and for cases where all terms of these matrices are actually time or constant terms. So if all numbers or all elements of the within these matrices are constant, then such systems are called linear time invariant. But if they are functions of time, like a, b, c, d, all are functions of time, then the system is called linear time variant system. So these are just yeah, the so based on the system type, the representation. So basically whether it is possible to represent the state space model in the system or not, that is so that decides whether it is linear system and non-linear system. So let us try to see. So these equations 1, 2 and 3, you can see this left hand side are basically the differentiation term, that is the x dot term, and the right hand side you can see rf by lf, that is a constant quantity. Rf by Lf, this is a constant quantity, this is also a constant quantity, because resistance and field winding inductance and resistance values, we can, these are the parameters of the system and can be reasonably as approximated to be constants. Again for the armature circuit, this part 1 by minus Ra by La, K by La, this is also a constant, and again 1 by La, this is also a constant. For the third equation, minus b by j, this is a constant, k by j is a constant, and 1 by j is again a constant. So the first equation, you can see that if is one state variable, vf is one input. So definitely it is possible for us to write it as say f11, some function of if and vf. For the second case, say f12, this is a function of the states, which states ia and omega as well as if, and input of and va, which is the input. So this can be written in this form. It is basically, the right hand side is basically a function of the state variables and the input. And similarly the third equation also, here also it is a function, some f13 of state variables like omega, if, ia, so omega, if, ia, as well as one input TL. So you can see all the equations 1 to 3, they are actually represented in the state. The first equation of the state space model is actually uh, is actually there, right? So is it possible for us to write these equations in the linear form, like ax plus bu, whether it is possible for us to do? Let us try to do that. So again, so this is our B matrix, and what is our input matrix? This is VF and VA. These are the input matrix. These are the inputs. So this is our, the first term is basically our x dot. This matrix is nothing but A matrix. This is XX, that is the state matrix, state variable matrix. This is B matrix, and this is U matrix, the input matrix. Right? Is it clear till now? Or is there any question?
Clear, sir.
Okay. So is it possible? Okay. So finally you understand that A into X, matrix multiplication of A into X, that has to be a 3 by 1 matrix, and your X is already a 3 by 1 matrix. So you understand A has to be a 3 by 3 cross 3 matrix, 3 by 3 matrix, in order to finally result in a 3 by 1 matrix, right? And for B, finally again B into U, that has to be a 3 by 1 matrix. U is a 2 by 1 matrix. So you will need your B to be a 3 by 2 matrix, right? That is the basic need. Now let us try to represent them. So the first term will get multiplied by if. So we can get, this is minus rf by lf. This is the one element of the A matrix. Second element, does it depend on IA? No, there is no term dependent on IA. So the second one will be 0. And the third one, there is no dependence on speed also. So the 1 3 term will also be 0. So our first equation is represented. This is a perfectly linear system, linear equation. So there is no non-linearity involved. So that is why we can represent the equation in this form easily. And the other part, the input part, so we will have the first term to be 1 by LF. 1 by LF will get multiplied by VF. So it is done. It does not depend on VA. So this term will be 0. So this is the representation of the first equation, which is there in the first row of the matrix equation. Now let us move towards the armature circuit equation. Armature circuit equation, there is no or let us start from the first term only. There is or this is multiplied by IA. So IA is the second entry in the state matrix. So we'll have to make the entry in the uh, in the second row, second column. So it is minus RA by LA, right? Now there is some complexity. So the input, let me complete the input portion. It does not depend on VF, so VF corresponding to that it will be 0, but it depends on VA, so there will be some 1 by LA term, it is there. Where we cannot, so there is some IF dependency and all, as well as there is some speed dependency, but they appear in a multiplication fashion. So it is clear that have we cannot have this second equation represented in this form. We cannot have the ax, so a multiplied by x separately, because two state variables are getting multiplied here. So that is why this equation actually is a nonlinear equation, and if if as well as omega both are varying, then it is not possible for us to represent the second equation in this format of linear state space model, like ax plus bu. The second equation cannot be written in that format, but that is where it helps, like for if we actually assume that we excite our field winding first and let it reach the steady state, then this if, whatever if we have, that will become a constant quantity. So if will be capital If, that will become a constant number. So with that assumption, it is possible for us to write the equation, the second equation, also in the format where uh, there will be no if dependency, so this will be 0, and the constant term appearing here will actually be k by La into if, right? So this is the second equation is only with the assumption of if has already reached steady state and there is no change in field excitation during the time of operation of the motor. So this is only with that assumption. Otherwise our DC motor is a nonlinear system. Only with the assumption that field circuit has reached steady state and there is no further disturbance uh, to the input of the field winding. So if also remains constant. With that assumption only, it is possible to linearize, or it is possible to assume, or possible to consider the DC motor model as a linear system and apply linear control theory on that. Okay, now let us write for the third equation. There is dependency on omega, so omega is the third term, so this will come as the third row and third column entry. So input, I'll write that. Okay, so sorry, uh, I have only taken VF and VA as the input, but in this case we are considering the TL also, the another input. So VF, VA and TL, these are the three inputs actually, as per our assumption that we have three inputs. Two are control inputs, the third one is a disturbance input. So the first equation, there will be a third zero term. This one is 1 by La, and this, there is no dependency on TL, so it will also become 0. And for the third equation there is no dependence on VF, there is no dependence on VA, but there is this 1 by J term appearing as coefficient of TL, so this will come here. Now let us, this term, the first term is represented minus b by j into omega as the third row, third column element. The last term is also represented like this, minus 1 by j into TL. The second term again you see that k by j is a reasonably constant term, but IA and IF both are variables, both are state variables. So again it is a nonlinear system, nonlinear differential equation. Um, it is possible to linearize it or represent it as a linear system with the same assumption as the previous case, that the field current has already reached steady state and there is no disturbance, there is no change in the field winding current or input voltage during the operation of the motor. So IF becomes a constant quantity and it becomes a function of the armature winding current only. So the first term again is 0, first term again is 0 because it does not depend on the field current as a state variable, and this one comes as k by j into if, right. So this becomes the first equation of the state space model of DC motor. So let me write that once more: TIF dt, TIA dt, T omega dt. So this is our x dot thing. Now our matrix, it is a 3 by 3 matrix and we have 3 state variables. First one is IF, next one is IA, third one is omega. We have the B matrix, again it's a 3 by 3 matrix, and we have 3 inputs. We have VF, we have VA, we have TL. So these are the 3 inputs. So what are the in the first row we have minus RF by LF 0 0. In the second one we have 0 minus RA by LA, and again what is the minus K by LA into IF. The third one 0 K by J into IF minus B by J, right. What we have here is quite simple: 1 by LF 0 0, 0 1 by LA 0, and here 0 0 1 by J minus 1 by J, right. So the first one is our x dot matrix, second one is our A matrix, this is our AX X matrix, this is the B matrix, and this is the input matrix. So this is the format. This is a linear system format, can be, so the DC motor model can be represented as a linear system if we assume that field dynamics have already settled down. So the field current is can be considered as a constant quantity, so that this comes as it comes within this element, uh, within these values. So you can see RF by LF, that is a constant quantity, 0 0 all are constant, 1 by LF is a constant number, 1 RA by LA constant again, K by LA into IF a constant quantity. This is also a constant, K by J into IF, B by J is also a constant number, 1 by J is a constant, 1 by LA is a constant number. So we have, so all the elements of A matrix are basically constant quantities, and all the elements of B matrix are also constant quantities. So this DC motor model, so DC motors, if we assume that the field circuit has already reached steady state, then it becomes a linear time invariant system. Now let us complete, for the sake of completeness, let us write the output equation also. Output, we only have one output, so this becomes our Y matrix. We'll have some C matrix, and this becomes our state matrix if ia omega, plus we will have some D matrix, and we have the three inputs Vf, Va and TL, right. Now omega, you can see that it is directly a state variable. It does not depend on any other state variable, and it does not depend on any of the inputs. So the C matrix in this case, so the C matrix, so it is a 1 cross 1, it is a 3 cross 1, final result has to be 1 cross 1. So this matrix, C matrix, in this case will have to be uh, 1 cross 3 matrix. This is a row matrix like this, right. And in this case also, it is the input matrix is a 3 cross 1 matrix, the final output is a 1 cross 1 matrix. So also, so this one also will have a row matrix like this, right. So the first one, so the speed is not dependent on if, so this is 0, this is not dependent on ia, it is 0, it is only equal to the third state, so there will be 1, and it does not depend on or it is not directly a multiple of any of the inputs, so it is 0 0 0. So this becomes the C matrix for our case, and this becomes a D matrix for most of the cases that you will encounter in electrical engineering control system, electrical engineering related controllers, machines, power electronics. Most cases this D matrix will only be a 0 matrix only. For certain cases the output, so for most cases the the desired output will only will be some of the states only. It can be one state or multiple states. In this case also we could always take ia also another output, because anyway we want to control the output current or the armature current in order to control the speed. So obviously it could be taken as one of the states also, and nothing much would change, only there will be another entry, another element in the output matrix, and there it will be one of these things will be 1, that's all. So for system perspective, this A matrix is most critical, because it tells us about the system, because it contains the parameters of the system, like Rf by Lf. What is this? This is nothing but the reciprocal of the time constant of the armature circuit, right. So armature circuit time constant is Rf by Lf. So this is reciprocal of that with a negative sign. Similarly, the second one, you can see this is the reciprocal of the time constant of the armature circuit, and the third one is nothing but the time constant of the mechanical subsystem, the reciprocal of that. So the diagonal elements, all these are time constants. So these include some information of about the system, and also the other terms like this one and this one. These are like the how two states are one is dependent on the another, like ia and omega, they are related in the equation. So that is represent that comes as this cross coupling or non diagonal elements, non zero elements, are the others as 0. So that means there is no cross coupling between the two, between those two, like if and ia are not directly there is no relation, there is no cross coupling between the two. And similarly omega and if, there is no cross coupling between the two, but armature circuit and speed, they have cross coupling in the form of back emf, as well as the speed that has cross coupling with respect with ia armature circuit as the torque, electromagnetic torque. So that is why these non diagonal elements are non zero, but the other non diagonal elements are 0. So this is, so because this is this A matrix is quite critical, and it includes it holds all the information regarding the system. So this A matrix is also called as the system matrix. So mostly it is the in state space based of study, it is mostly the study of A matrix only, and this is the most important matrix uh, that holds critical information regarding the system. Is there any question regarding whatever I have discussed till now? Okay, so we have learned about the first one is the differential equation model, which anyway we know, and the second one is state space model. In this particular format we represent the system, and we understood about the state variable matrix, input matrix, output matrix, then we represented them. We also understood, based on our ability to represent the state space model like these two equations in as uh, separate matrix multiplication of state matrix and input matrix, based on whether it is possible or not. Based on that, the system can be or whether the system is a linear system and non-linear system can be told based on that. If it is possible to represent the system as ax plus bu and cx plus du format, then it is a linear system. If it is not, then it is a non-linear system. Again, if the matrix elements a, b, c, d all are constant quantities, then it is a linear time invariant system. If the elements are functions of time, then they are linear time variant system. Then we represented the DC motor model in the state space format. So this is the representation. We understood that the armature field circuit is a perfectly linear circuit, but the armature and the speed, that is the mechanical subsystem, those are not linear but nonlinear differential equations. But with the assumption that field circuit has already reached steady state, so that we can have if has already reached capital If, that is a constant number. With that assumption, uh, it could be represented as a linear system. Then in the armature circuit there is only a back EMF term, so only the speed variable, the state variable speed is there, its effect is there, so it comes there. And in the speed, the effect of torque, electromagnetic torque is there, which is proportional to the armature current, so it comes. Then next we represented the output circuit output thing also, and after that we had a discussion on the A matrix, that is the system matrix, where we saw that the diagonal elements actually contain the reciprocal of the time constants of the individual um, differential equations, which also represent field circuit, armature circuit, or mechanical subsystem. And there is cross coupling. So for wherever there is no cross coupling, like there is no cross coupling between the field and the armature, so these are 0. There is no cross coupling between the mechanical and field, so these are 0. So field is 1, armature is 2, speed is or mechanical is 3. So 1 1 represents the time constant, reciprocal of the time constant of the first one. 2 2 represents reciprocal of the time constant of the armature one, and 3 3 it represents the reciprocal of the time constant of the mechanical one. There is no cross coupling between field and armature, that is 1 2. So the elements 1 2 and 2 1 both are 0. There is no cross coupling between field and speed, the mechanical, so 1 3. So the elements 1 3 and 3 1 are 0. But there is some cross coupling between the armature and speed in terms of, so the effect of armature current comes as electromagnetic torque in the mechanical subsystem. So this 2 3 and 3 2, both these are, this is basically 2 3 and this is 3 2, both these are non-zero quantities. So it includes all the information of the system, so it is called as the system matrix. That's all that we have discussed till now. So let us start with a brief uh, introduction to what is difference equation model. Only the basics we will discuss, and afterwards we'll conclude, will continue in our next one. So difference equation, that is a representation or a discretized form of the differential equation model. So we have different variables. So say we have some state variables whose values are changing in some pattern. I don't know. I am just indicating some continuous time. So this is some x and this is time. With change in time, the value of x is changing. So it's a smooth function. It's a continuous function of time, right? So it is a continuous time representation of the state variable. But as soon as we go into the difference equation model or discretized form, then we need to we cannot have information about the continuous, or we do not have information of x at all instance of time, but instead of that we will have to do some sampling of the quantities, and we will hold the information about the state variable at those specific sample. So say this is the first sample, so this value is stored. This is the second sample, this value is stored. This is the third sample, this value is stored. Similarly, wherever there is some sampling happening, whatever is the value of the state variable x at that sampling instant, that value is known to us. Whatever happening between the two sampling, we don't know. So these are different sampling instance, and say this is k, this is k plus 1, this is k plus 2, whatever. So this the value of x can be written as x of k, this is x of k plus 1, this will be x of k plus 2. So like that it will be. So actually the discretized representation of the same state variable will be like this. You will not have any information of x in continuous time, but you will have only information about it at the kth instance. So kth instant the value is this, k plus 1 instant the value is this, k plus 2 it is this value, k plus 3 it is this value, whatever. So whatever are the sampling instance, we will have some information about the variable like this. What is the value of the state variable in between these two, that is in between this instant and this instant, that is not known to us, right? So wherever we discretize the continuous time signals, we do some sample and hold, that is we look at what is the value at a particular sampling instant, and we hold that value and we remember that information. So this is that information, and we represent the state variables like this. That is basically your difference equation, or basically this is the discretized form of the state variable. Now obviously this sampling, whatever samplings are being done, so k plus 1, k plus 2, they have some frequency. So we are doing it after a constant amount of time. So whatever there is time between the two, that is a constant, that is a fixed time difference between the two sampling. That means whatever sampling we are doing at it at a constant sampling frequency. So whatever is the this is say one sampling instant, this is the next sampling instant. So this is say time t equal to t1, this is time t equal to t2. So whatever is the time difference between the two, t2 minus t1, this is called as sampling period, and 1 by ts is also called as fs. This is the sampling frequency, right? So these are the basic things, basic terminologies regarding discretization of a continuous time signal. There is a sampling period, that is after what time the sampling is done, and there is the sampling frequency, what is the frequency of the sampling that is done. Now suppose there are other, so you understand that we need to, in order to sufficiently represent the system, we need to have a high enough sampling rate. Suppose the signal that we want to represent is a sinusoid of some frequency, say some hertz. So this is t1, say. So time in say this is a 50 hertz signal, so this will be 20 millisecond. This is actually 10 millisecond, this is 0. So this is some signal, this is time. Now we want to sample the system. Now let us say we sample at 50 hertz only. So we sample it here, it is the 0, and again the next sampling we do at 20 millisecond, this is also 0. So if we sample the sinusoidal signal of 50 hertz with 50 hertz sampling frequency, we always have a 0. We do not see the variation of the sinusoid. Now it also depends on what instant we do the sampling. We are doing the sampling at the same frequency only. Say we sample at this instant, so this is the value. Again after at 50 hertz we do the next sampling here, that is this green arrow to green arrow, this will be 20 millisecond. So the value will be this. So for if we sample the sinusoid of 50 hertz with 50 hertz sampling frequency, then you see that our sampling, our representation in the discrete domain is not correct, because actual signal is a sinusoid, but our discretized signal is a constant quantity. For the red one it is constant at 0, for the green one it is constant at some value, this value, and so on and so forth. It depends on the sampling instant. Now say we sample at twice the frequency. Let us say we sample it at twice the frequency. This is x, this is t. Now say first we sample it here, say we sample it here, then 100 hertz, so we sample it here, again we sample it here, again we sample it here. So here you can see in 2 cycles we were sampling only twice, here in 2 cycles we are sampling 4 times, but still you can see that it is actually 0 if we sample it like this. Now if we actually sample at some other instance, say we sample it here, so it is this value, we sample it here, so it is this value, again we sample it here, it is this value, and again we sample it here, this is this value. So in this case if you see the red dots, some information is there, like at least we know that obviously it depends on the sampling instant. It may completely make us fools if we sample at the zero instance, zero crossing instance. But if we sample at any other instant, some variation, that at least it is a bipolar signal changing its sign from positive to negative, that information at least is there. But still we do not know that the signal is actually a sinusoidal signal. We have no information about that, because your even if your signal could be this also. Say your actual signal is this. If you sample the black signal, or if you sample the blue signal, there is no difference. Your discretized form cannot differentiate between the blue signal and black signal based on 100 Hz sampling frequency at that instant. So you understand, the message is, when we are discretizing the system, or discretizing the a signal, a continuous time signal, the sampling frequency has to be high enough to represent the continuous time signal properly in the discrete time domain. So at least if we have a sinusoidal signal like this, at least say if we sample 10 times, so we sample it 9 times here, so 1 2, so at least say 5 times, 3 4 5 6 7 8 9 10 11 12 and again 13. So at least we are sampling it twice, 12 times within the sampling period. So what is the discrete representation? Let me use orange color. So the first one, this is this. Second one, this is the sample and hold value. This is this value here. This is this value here. For this instant, this is this value. Then again we have this value. Then we have the zero instant. For this instant we have this instant this value, this instant this value. Here it is this, here it is this, and again here it is this. So the orange one is the discretized representation of the same signal. So the blue one is the continuous time signal, and the orange one is the discrete time representation. So in this case you can see that the discretization does not take away or the discretization holds the information about the signal. You can it can close it, it is close to a sinusoid. Actually it's close to a sinusoid, or some variation of the sinusoid is actually seen. So the information is, if when you are sampling a continuous time signal, you are sampling a continuous time signal, and you are going to the discrete time signal, your sampling frequency has to be high enough. Typically there is something called as Nyquist criteria that tells that whatever is the fastest frequency or the highest frequency of the signal of interest, the sampling frequency at least has to be twice the sampling frequency, twice the highest frequency. That is also known as the Nyquist criteria. But you saw that if the signal is of 50 hertz, and if we sample at 100 hertz, still the information may not be sufficient. Like this red dots, we were sampling at 100 hertz, but we could only say that there is some variation from positive to negative and positive to negative, but we did not have accurate information of the system. Only if we sample the system or sample the signal at least at 10 times compared to the highest frequency of the signal. So for this case this was 100 hertz or 50 hertz, we sampled at 12 times the frequency, that is 50 times 12, that is 600 hertz. At least when we are doing at 600 hertz, we retain some actual information about the system. So whenever we are going for digital representation or discretized representation of a continuous time signal, the sampling frequency is extremely crucial for us to decide. We have to have some idea about the highest frequency of our interest, and our sampling has to be at least 10 times that. If it is better if it is more, at least 15-20 times. If it is 20 times, you can understand that there will be yet another sampling between the two sampling instance of the orange one. So there will be another one. So it will be further refined as a sinusoid, but at least it has to be more than 10 times the frequency of our interest. Yeah, uh, this is the point with which I'll close. Any question? Okay. Good night. We'll continue on the next day.